This is section 8.4. So in 8.4, we learn about hydrohalogenation, which means adding a hydrogen and a halogen across a double bond as shown here. So if you perform this reaction on 1, 2, 3, 4, 5, 6, 3 hexene, you add HBr to 3-hexene at a low temperature, you get HBr substituted hexene in good yield. And it's a good reaction, but this is a symmetric substrate, meaning no matter where the H and Br are, whether here or flipped, it's the same molecule. What if we had to worry about the regiochemical outcomes of this reaction? Well, in that case, something interesting really happens. If you have this molecule here, and you add in HBr to it, you get hydrohalogenation that always happens in this manner. You have the H that always ends up here, and the bromine that always ends up here. And this is called the Markovnikov product of this reaction, because Markovnikov was a very smart chemist who found out that there are some general rules about hydrohalogenation reactions, in that if you add a strong acid like HBr to an alkene, the hydrogen will always go on the least substituted carbon, and the halogen, the X, here it's bromine, will always go on the most substituted carbon. And how this happens is shown here, where first you protonate the alkene with the acid, kicking off the bromide to give you a carbocation that is now able to be attacked by the bromide to give you the hydrohalogenation product. So let's have a look at the reaction diagram for this reaction so that we can understand it a little better. Here's the reaction diagram of a hydrohalogenation process. There we are. And you'll see that the products are indeed more stable than the reactants, which is good. And you'll also see that there's an intermediate here, this carbocation, just like we saw for unimolecular reactions. So it takes a large amount of energy to protonate the alkene, but once you do, it takes a lot smaller amount of energy for the bromine to act as a nucleophile and attack the carbocation, which you would expect because bromine is a strong nucleophile, and it would be very attracted to a carbocation to give you our products. So because EA2, the activation energy listed EA2 here, the first step, is higher in energy than EA1, it's the slow step. So the question is, why is it Markovnikov addition? Why is it always, why does the addition of H to an alkene always happen this way, where the least substituted carbon has the hydrogen and the most substituted gets the carbocation? And the answer is, of course, rearrangements. So if you remember from the rearrangement section of chapter 6, one of the fundamental reactions of organic chemistry, anytime you have a secondary carbocation, it's going to want to rearrange using a hydride or a methyl shift to the tertiary carbocation. And that's what happens here, is even if you formed a secondary carbocation, the rearrangement happens so fast that you could essentially just say you always get the tertiary carbocation. So what about the stereochemistry? Does this happen in a stereochemical way? And the question is, or the answer is not really, because if you add HCl to this alkene, what you will get is a chiral product. But the problem is that you will get equal amounts of both isomers, both enantiomers, and we call that a racemic mixture. And the reason why you get a racemic mixture is because if you think about this planar carbocation, and we're kind of looking down on it, it has a top face here in red and a bottom face in blue. The nucleophile can approach it from either direction, from the top or the bottom. And so there's equal probability that you'll run across both stereo isomers, and so there's no enantio enrichment. There's no enantio selection that happens there. So then we talked a little bit about rearrangement. What about if we had a substrate that could not do the reaction without rearranging? Like, let's say you have this one. You generate the Markovnikov carbocation, like we know that we should. But before you can do the final nucleophilic addition, there's a rearrangement that happens because rearrangements are a lot faster than nucleophilic additions. So because they're a lot faster, anytime that the molecule will rearrange in this manner, it's going to. So instead of getting the normal hydrohalogenation product like you would expect, you have the nucleophilic attack on the rearranged carbocation to give you kind of a strange looking product. But the point of this is that anytime you can have a rearrangement to get a more stable carbocation, that will happen. So keep on the lookout whenever you're doing a reaction and make sure that you're not missing some rearrangement step just based on carbocation stability. And alkenes aren't the only molecules that can undergo hydrohalogenation. Alkynes can as well. And this information comes from page 414 to 415 in your book, which is actually chapter 9. As we go through some of these reactions, alkynes do a lot of the same chemistry as alkenes, so we'll cover them as well at the same time. So in this case, if you have some alkyne and you treat it with exactly one molecular equivalent of HBr, you will also, of some HX, where X is a halogen, you will also get addition across the double bond. And the mechanism is pretty much the same, except for the carbocation looks a little different. It has a double bond instead of the single bonded carbocation that we're used to. But this reaction goes very well, even so, and you get between 60 and 80%. If you treat an alkyne with excess HX, you end up getting two halogens on the same alpha carbon. And that happens because the mechanism is pretty much the same, but now you're making two carbocations, and the second carbocation also wants to be in that same Markovnikov configuration. So you'll make an alpha carbocation here instead of the carbocations that we're used to seeing. So this was section 8.4.